Okay, all right. So happy Friday, happy week 5 Friday. We are, I guess, halfway through the quarter now, so just another 5 weeks to go. Okay, so yes, you should be meeting with your groups, picking out your data, and figuring out what you guys are going to do, and you want that ready for your proposal meeting. So it looks like most of you have signed up for a time slot on the group sign up page. So if you haven't done so, I think there's maybe 2 groups remaining that still need to sign up for a time slot. Make sure you do that. And then, I think what I'd like to do maybe during 6th and 7th week is to do some example, data analysis with some of the group's actual data. And so we will encounter, issues with the data and things that need kind of cleaning up and whatnot. And so, during your proposal meetings next week, I'm going to ask for some volunteers to kind of volunteer bringing, their data into class, and then we will spend some class time kind of working through that particular group's data and doing some basic some analyses and exploration as a way to kind of one, to help out that group and provide guidance to that particular group, but also my hope is that it will serve as an example for other groups to kind of see what kind of questions and what kind of things they can be exploring. So next week during your proposal meetings, I might ask for some volunteers regarding, can we use your data for some, in-class demos. And then, I'll ask that group to do just a little bit of preparation before they come to class on, say, Friday or Monday or Wednesday of the following week. Okay. We are going to take a look at some, foundational statistical concepts. So far in our course, we've been spending a lot of time on just learning the tools in R, just learning how to import your data, learning how to kind of calculate some summary values, learn how to create graphics and visualizations. And these are all going to be very important because the way we interact with our data sets requires the use of R. Our data sets have kind of, a lot of times we're working with big data sets where, using tools like Excel just isn't going to be enough. Okay. And again, I love Excel and I think you can do a lot of great things with Excel, but the tool we're going to be using is R, and we spent a lot of our course kind of just going over how to interact with the data through R. Okay, now that we're hopefully starting to feel a little bit comfortable interacting with the data, we can start asking statistical questions. Okay, we can start asking statistical questions, and so one of the first questions that we want to ask is there a difference between groups? Okay, and so we're going to we're going to start off by comparing groups, and we'll look at this kind of one question and a corresponding what we call hypothesis test that goes along with it, and we'll look at maybe a couple other questions next week. We'll do some time doing some data analysis, and we'll kind of be going back and forth between statistical questions and exploring data and looking at some examples. All right, and all of this with the hope of giving you some exposure, so you feel comfortable working with data and comfortable asking these statistical questions. Okay, so we're going to start off with just some foundational concepts for comparing groups, and this is just some made-up scenario, along with made-up data. Okay, so this is not real data. These are numbers I made up. This is just some pretend data set, okay? And so we're going to pretend we have this data that comes from an experiment, okay? And it's an experiment involving batteries. And I don't know if you ever had this question, right? You go to the I don't know, the supermarket, or the you go to Walmart or Target or whatever, and they have batteries, right? And they have like Duracell, Energizer, Rayovac, and then like store brand, right? And so like if you were to go to say like Walmart, they sell these generic kind of store brand batteries, and they're usually like super cheap, and you wonder like, are these any good? Right? Here Target has their kind of in-house brand, and you just go like, okay, well, is this any good? And I don't know, how much are these batteries here? Okay, so Target's are $8.99 for 10. Walmart's is $3.68 for 10, or eight of them. Okay, so Target's charging more, and you kind of wonder like, oh, I've never heard of either of these brands. Are either of these things any good? And so let's say somebody ran an experiment, okay, and we'll just call these brand A and brand B, not to actually pick on Walmart or Target. And again, I've just in this example we have fake data. Oh, I'm sorry, I need to upload the data set to Canvas. Okay, so I have statistical foundations. Let me upload that CSV file. Batteries.csv. Okay, so we have this CSV file with battery information, and I can open that up, and it's just this really tiny, simple data set where I just have brand A, and these are some numbers, and brand B, and these are some numbers here. Okay, and so the data is the result of this, again, fictional experiment, and we're going to say the experimenters, what they did was they just built like this little electric contraption. Basically like you put a battery in the thing, and maybe it powers a light bulb or a little motor or something, and it's designed to kind of like drain the battery at a constant rate, and it measures the voltage. And so as the battery gets used, its voltage drops, and you can talk to different people, but one kind of rule of thumb is like once it drops below 10% below its stated voltage. So, the battery is supposed to be 1.5 volts, and once it drops below 1.35 volts, you might say it's no longer performing at level. Okay, and so we'll say, okay, we're going to see how long did the battery last until it hits this voltage of 1.35 volts. Okay, and again, just because of different random factors, one of them could be just the manufacturing process. These batteries end up not 100% identical. You're going to get a little bit of variation between the runtime. And so we're going to say, okay, so this one battery lasted 132 minutes until it dropped. This battery lasted 122 minutes until it dropped below 1.35. This battery lasted 127 minutes before it dropped to 1.35 volts, right? And we got numbers for brand A and numbers for brand B. And the question is, do these two brands have different things? Okay. Here, the setup I have here is, you have a friend, and the friend says, you know what? A lot of these store brand batteries, they're just made at the same factory. I don't know if you've heard of things like that, right? They say, oh, there's just some random battery factory that just produces a whole bunch of things, and all they do is they just change the sticker. They just change the label, and then they sell them to different companies. And you go, oh, okay, so maybe these internally, these are the exact same battery, and they just have different labels. Or maybe they're actually different. Who knows, right? And so we're kind of exploring this question. And so we say, okay, we got these two brands. These are the numbers, and we want to know, okay, is there a difference between the batteries? Okay, so I'm going to start off to get into our data analysis. I'll load up the tidyverse. Okay, and then I'm going to read in batteries.csv. All right, so I'm going to just store into R, into this data frame or tibble batteries. We're going to do read underscore batteries.csv, and then it just says, okay, we see two two columns, brand A battery, brand B column. And I say, okay, what does my data set look like? It's exactly what we have in the CSV file. Okay, and so we've got 12 batteries from brand A, and these are the numbers. 12 batteries from brand B. These are the numbers, and we just want to know, hey, is there a difference in these averages? And we can see, oh yeah, you know what? Sometimes the batteries last long, and sometimes the batteries don't last very long. So in order to kind of work with this, we have to do a little bit of data manipulation, right? So if I wanted to use like summarize, and I wanted to group by the variables, you know, one thing I need to do is I need to pivot my data. Okay. And I suppose I could have also created like a little plot, but here I'm going to pivot the data. So I'm going to take the original batteries data set, and what I'm going to do is I'm going to take these, we have the numbers stored in two columns, and what I'm going to do is I'm going to pivot it longer, so all the battery values are in one column. Okay. So we're going to say pivot the brand A and brand B columns, and we're going to take the name of those columns, the column headings brand A and brand B, and put that into a new column called brand, and then the values we're going to put into a column called runtime. And so now I just have one column of runtime, and we can see the original table had 12 rows, and now that I've pivoted them longer into one column, I now have 24 rows. Right? Does this kind of make sense, what I'm doing? And then I arranged it by brand. So the first 12 will be brand A, the last 12 will be brand B. And then what I want to do now is I just want to calculate, okay, what is the mean of brand A and what is the mean of brand B? Okay. And so the mean of brand A is 123. The mean of brand B is 129. And we want to know, is there a difference? I probably should have maybe included a little plot, right? But maybe I'll add that in the notes or something. Okay, but basically, so brand A, when we measured 12 batteries, the average was 123 minutes. Brand B, the average is 129 minutes. And so the question is, what does this tell us? What does our data tell us about brand A and brand B in general? Okay, so this is kind of our first statistical question. Okay, because back here, I would argue that calculating the mean, what is the average brand time for brand A, what's the average time for brand B, is not really a statistical question. That's just calculating the mean, right? And you could have done this in 5th grade, right? In 5th grade, we could have said, hey, what's the mean for brand A and what's the mean for brand B? And you could have done this, okay? But now we want to ask this statistical question, and that is, if my data says brand A has an average of 123 and my data says brand B has an average of 129, which is slightly different, what does that say about brand A in general and brand B in general? Okay, and there's kind of, I'm going to say there's two possibilities. One is that in general, brand A's runtime and brand B's runtime are different. And in our case, we would argue that brand B has a longer runtime than brand A, right? And kind of indicating that, that maybe they're coming from different factories, okay? Or another possibility is that what we're getting is just kind of random, right? That maybe brand A and brand B do come from the same factory. There's no real difference between these batteries, but I selected the batteries at random, right? So we're going to say, in general, both brands have the same mean runtime. If we were to kind of trace the supply chain back to the origin, we would find out, they're actually the same. But just kind of by random chance, when I ran this experiment, when I selected 12 batteries labeled brand A, I happened to get kind of a bad batch where the average performance was a little bit lower, and I happened to get a slightly better batch when I picked the brand B batteries, and maybe that's why we're seeing a difference in runtime. Okay, does that kind of make sense? The question I'm asking. So now I'm asking, is this an actual thing? Brand A has this average and brand B has a different average? Or is this kind of just a result of like randomness, right? And this is kind of a core concept and a core reason why we want to do statistical tests, is we want to be able to distinguish between this is an actual thing that's happening versus, oh, this is just like a slightly weird random thing that's happening, okay? And so here are just a couple other examples not related to the batteries of like, is this a random thing, or is this a real thing going on, right? So what would you think if this happened? You flip a coin 20 times, or your friend or somebody says, I flipped the coin 20 times, and then they tell you it landed heads only 5 times out of 20 flips, okay? So you think, well, okay, if it's a fair coin, we should get something like 10 heads, right? Out of 20 flips, we're expecting around 10. We know there's randomness, so if they got 11 heads, we wouldn't be shocked. If they only got 9 heads, we wouldn't be shocked. They're only getting 5 heads out of 20 flips. And so the question is, all right, is something wrong with the coin, or something strange about their flipping technique, and that's why they're only getting 5 heads out of 20? Or did they just have like this weird luck and got 5 heads out of 20? What do you guys think? Just gut instinct. Weird luck? You think it's weird luck? I don't know. I mean, there's no right. I mean, this is just a made-up scenario. Okay, this is just a made-up scenario. So and it could go either way. It could be weird luck, and if it's weird luck, something like this would happen maybe with a 2% probability. Okay, if you do the calculations, or it could be like, oh yeah, maybe the reason why we're seeing only 5 heads out of 20 is like something's weird with the coin, or they're doing something funny when they're flipping. Okay, and maybe that's the easier explanation, right? If it was only like 2 heads out of 20, I think it would be a lot easier to kind of say. We'd say, okay, technically, can you get 2 heads out of 20 with weird luck? Technically, it's possible, but what's the probability of that happening? It's like so incredibly small that we're going to just say the easier explanation is something weird is going on with the coin. That's the easier explanation for us to swallow than to say, oh no, you just got some really, really weird luck, and that's why you got only 2 heads out of 20, right? Okay, so that's kind of like not a very important discussion, but maybe a more important context where you want to determine between actual phenomenon versus a random fluke is, let's say you're working for a pharmaceutical company, okay? And there's experimental medication. They run clinical trials, okay? And whenever you do a clinical trial, let's say, somebody has some kind of condition, some kind of illness, some kind of ailment, and you give medication or placebo or whatever it is you're looking at, some people are going to get better and some people aren't, okay? That's just going to happen. Whether you intervene or not, sometimes people get better and sometimes people don't, right? And what we're hoping for is that intervention helps increase the number of people that get better, okay? So they're trying out this new experimental medication. They give some participants the medication. They give other participants the placebo. And for users of the medication, some patients experienced improvement in symptoms and some did not. And we're going to say 65% improved. For the placebo users, some patients experienced improvement and some did not. And for the placebo users, only 55% improved. So we got 65% versus 55%. And the question here is, does this mean the medication is more effective than placebo? Okay. Or is it possible that this difference is just kind of by randomness, that just that I could have given, you could imagine some other scenario where I gave everybody placebo, okay, but I gave some people like, a red t-shirt and some people a blue t-shirt. And just by random chance, the people who got red t-shirts, 65% improved. And just by random chance, the people who got blue t-shirts, only 55% improved, right? We could imagine some, that could have happened by random chance too, right? And maybe it's really unlikely for something like that to happen, or maybe it's entirely possible, right? So there's kind of this fundamental question, and I would say this is at the heart of a lot of statistics is we have this desire to distinguish between what's actually happening versus what's a random fluke. Okay, let me give you, I haven't given you any view quiz answers, right? Okay, first one today is the letter D. D as in dog. D as in dog is our first view quiz answer. All right, so to test this, or to ask this question and try to seek an answer of is it an actual phenomenon versus could it just be a random fluke, we run something called a hypothesis test. Hypothesis testing we can think of as some kind of framework that are going to help us make conclusions about the population. And in our case, for testing the batteries, the runtime of 2 brands of batteries, we're going to start off with a very simple hypothesis test called the t-test, the 2-sample t-test. I've got 2 samples of data, brand A batteries, brand B batteries, and we're comparing the means. We do something called the t-test. There's a whole bunch of other hypothesis tests that allow us to kind of compare proportions, compare multiple categories, things like that. And so we'll explore some of those ideas. In a classical statistics course, did anyone of you take like AP stats or something like that? Okay, so if you did, you probably learned like a lot of like the normal distribution and the t-distribution and how you do stuff, how to run these tests. We're going to I'm going to kind of skip a lot of that classical stuff and kind of go straight for like running the test on your computer and understanding what its output means. Okay. So when we do hypothesis testing, the reason why we call it hypothesis testing is we make a hypothesis. Our research question that we have, we turn it into basically a statement or a claim. We call that the hypothesis. And it's a testable hypothesis. We call this thing the null hypothesis. And for it to be testable, for us to be able to test the hypothesis, it has to be a very specific claim. Okay? We can't make vague claims because vague claims can't really be disproved, right? Because if you make some, like if you were to see like a fortune teller or something, right? And they only just make vague statements, you can't really prove them wrong, right? They say, oh, something interesting is going to happen in the next week. Okay, well, that's so vague, we can't really do anything about it, right? If you make something very specific and say, hey, at this day, at this time, this exact thing is going to happen, we can test to see if that actually comes true or not. Okay. Similarly, for hypothesis testing, we have a very specific claim. And the general form of the t-test is that you have 2 groups, 2 populations, and the mean of population 1 is, we use the symbol mu1, and the mean of population 2, we use the symbol mu2, and we're saying these 2 populations, these 2 groups have the same mean. Okay, in the context of the battery, we're saying we've got brand A, we have brand B, and the average runtime of all brand A in general and the average runtime of all brand B in general is the same, that there's no actual difference between brand A and brand B. Maybe because they're coming from the same factory. We're not even claiming anything about the factories. We're just saying that the average of all brand A is this number. The average of all brand B is the same exact number. Okay? And so symbolically, mu, okay, so I don't know if you've seen this symbol before. It looks like a little U, but it's got like this little leg in the front. That's the symbol we use for the mean, okay? It's called mu. And we're going to say mu of brand A is equal to mu of brand B, okay? And we call this H0 for the null hypothesis, or 0 kind of being the null. H0, the null hypothesis, is that the mean of A is equal to the mean of B regarding battery runtime. And to test this, we make the assertion. We say let's assume this statement we made here, let's assume it's true. Let's assume brand A and brand B do have the same average runtime, right? So let's imagine what the world looks like if brand A and brand B are identical. Then what should my data look like? In this, we have this null hypothesis, and we say if this were true in this kind of hypothetical situation, right? So hypothetical, same root as hypothesis. In this hypothetical situation where brand A and brand B are identical, what should my data look like when we do a random experiment, okay? And what we're saying is that, okay, I recognize that I'm selecting random batteries, okay? And, if I ran the same exact experiment the next day, even if brand A and brand B are exactly the same, I wouldn't expect my average for sample A and sample B to be exactly the same, but what would I expect? I expect them to be very, very similar, right? So I would expect the mean runtimes for the two groups to be equal to each other, or at least fairly close to each other, right? So if brand A and brand B are identical, whenever I do a random experiment, I expect the average of brand A and the average of brand B in my data to be pretty close to each other. And the question now boils down to, well, in my data, I got 123 for brand A and an average of 129 for brand B. Are those numbers close to each other? Or are they different enough for me to say, this is not why. This is not the scenario for my data, okay? So, the two samples I have don't have the same mean. They have a difference of 6 minutes between their averages. And the question is that different, or could that just be because of randomness? All right? Does that kind of question make sense regarding the thing here? Okay. So we know individual batteries have different performances. We know the batteries are selected at random, and so the mean, that means the sample averages are affected by kind of the random selection process. And so we take that into account and we say it's impossible. It is possible that kind of this random selection process, we end up with one sample where you have a longer runtime. We end up with another sample with a shorter runtime. We only have 12 batteries, so could this happen? And the question is, all right, let's assume brand A and brand B are actually like the same, right? That there's actually no difference between brand A and brand B. It's really all the same batteries. We're just changing the stickers. If that were the case, what's the probability that just from random selection, I end up with one mean where it's 123 and another mean where it's 6 minutes higher at 129, okay? So we're going to ask this question. What is the probability that randomness could produce a difference of 6 minutes or maybe more if the null hypothesis were true? And the probability of this data happening, we call the p-value. So here's this definition, okay? The p-value is the probability of observing the statistic in our data or something more unusual if we assume the null hypothesis were true, okay? In the context of a problem, the p-value is the probability of observing a difference of 6 minutes between sample means if population 1 and population 2 have means that are equal. So if brand A and brand B are really in fact the same, they have the same average, what's the probability that just kind of by selecting batteries at random, I end up getting a 6 minute difference? And before we do any calculations and run the test, I want us to think about what it means if this probability, this p-value, this probability of getting our data, what it means if the probability ends up being small versus what does it mean if the probability ends up being big? Because those are kind of what could happen, right? So one is we do our calculations and it says, you know what? If brand A and brand B are the same, when you select batteries, most of the time you should get differences of 0, maybe 1 minute, maybe 2 minute differences. And the idea of getting a 6-minute difference is really, really, really unusual. So that's one possibility, okay? That we're expecting a difference of small differences, and getting a 6-minute difference, the probability of that is really weird, okay? Again, it's like flipping the coin 20 times. We're expecting maybe 10 heads, maybe 11, maybe 9. And the idea of getting, say, 2 heads out of 20 flips is really, really, really weird, okay? That's one possibility, is you do your calculations and you say, oh, you know what, getting 2 heads, really strange and unusual. And maybe your calculations say, hey, getting a difference of 6 minutes just kind of from random selection, maybe that's a really unusual thing, okay? And so, well, in our data, that's what we got. We got a difference of 6 minutes. And so what does that mean? Okay. Well, in this case, the fact that we actually got 6 minutes and our calculations say 6 minutes just shouldn't really happen, is really unlikely to happen, then we say the reason why we got 6 minutes is because this initial assumption was wrong, okay? The assumption that we used that said brand A and brand B are the same, that's wrong, and that's why we're getting a difference of 6 minutes, okay? Because if we assume brand A and brand B are the same, our calculations say 6 minutes just shouldn't happen. The fact that it did happen indicates to us that, you know what? Brand A and brand B aren't the same, okay? Is the logic there okay? It's the logic is kind of like, if it's a fair coin, can you get 2 heads out of 20 flips? Again, it's not impossible, but it's really unlikely. If you flip the coin 20 times and you only get 2 heads out of 20 flips, then the easiest explanation is that it's not a fair coin, rather than saying we have this really unusual luck circumstance, okay? And here we're going to say if our p-value ends up small, we're saying that if brand A and brand B are the same, getting a 6-minute difference is really weird, shouldn't happen. So the fact that we got this indicates to us that our initial assumption that brand A and brand B are the same, that's wrong, okay? And so in that case, we reject this initial claim made by the null hypothesis that brand A and brand B are the same, okay? The other possible outcome is we do our calculations and we get a p-value that's large, all right? So maybe we go through our calculations and we say, you know what? Getting a difference of 6 minutes, it's not that weird, okay? If brand A and brand B are the same, sure, we expect something where the means are similar to each other, but you know what? There's kind of enough variety, enough variation in the numbers that, you know, getting a difference of six minutes, that's not that weird, okay? It happens with a fairly high probability, okay? And therefore, that indicates to us that we don't have any reason to conclude that brand A and brand B are actually different. So that's another possibility, right? So it's kind of like you flip the coin 20 times and maybe you get 12 heads. Does that mean something's wrong with your coin? And you go, well, you know what? If I had a fair coin, sure, I would expect around 10 heads. But you know what? A fair coin could land heads 12 times out of 20. It's not that big of a deal. And that's what we're saying here. When I do the calculations of the probability, getting a difference of 6 minutes, not that big of a deal. We're getting a large probability, okay? It's a fairly large probability that this could happen just kind of by random process. And therefore, I don't have any reason to believe that brand A and brand B are actually any different. Okay, so those are the two potential outcomes. We could end up with a small probability for our data. What's the probability of getting a 6-minute difference? And it could say, hey, the probability of getting a 6-minute difference is really small, indicating to us that the fact that we got 6-minute difference is that our initial assumptions are wrong. Or we do our calculations and the probability of getting a 6-minute difference is pretty high, and we say, okay, well, I guess our data could be the result of just randomness. Okay, does that kind of make sense? And so how do we decide whether our probability is big or small? We use something called the significance level. It's just an arbitrary line. It's an arbitrary line in the sand. And we say, hey, if our probability ends up larger than this number, then it's large. And if it ends up smaller than this number, it's small. Let me give you your second view quiz answer. Second view quiz answer is the letter C. C as in cat. C as in cat. Okay? So is our p-value large or is our p-value small? We compare it to just this kind of arbitrary line. It's called their significance level. The symbol we use for a significance level is alpha. And if our p-value ends up less than alpha, so if alpha is, say, 5%, then our p-value is considered to be small. And that means our data is unlikely to be observed if the null hypothesis were true, and so the fact that we did get this data leads us to reject the null hypothesis. On the other hand, if the p-value ends up larger than alpha, we say our p-value is large. Even if the null hypothesis were true, our data is not that unusual. It doesn't really contradict the assumptions there. And so we don't have any reason to believe the null hypothesis is wrong, and we would not reject the null hypothesis. Okay, choice of significance level is arbitrary. Most commonly, we use alpha equal to 5%, significance level of 5%, and that's kind of our threshold. Is it higher or lower than a 5% probability? But you can also use a significance level of, say, 1%. You could use a significance level of, say, 10%, but I would say that's not very common. 5% is usually kind of the largest we go. Okay, so let's kind of just revisit our data. And so here I just did batteries grouped by brand. We'll do a summarize. And we're going to say, let's calculate the mean. Again, the mean of brand A is 123. The mean of brand B is 129. Let's calculate the standard deviations. And we have 12 of each brand. Okay. And we can say, you know what, there's a good amount of kind of variation. Standard deviation is like how different are the numbers from each other. And we say, oh, you know what, there's a decent amount of variation. How so the numbers are kind of different, you know. So we'll run the test, okay? So we're going to say mu of A is the mean runtime for all batteries from brand A. Mu B is average for brand B. And again, we're not able to actually measure all the batteries from the factories. Okay, we're not able to measure all of brand A. So we have to kind of make guesses based on just the data that we have, and we're hoping the data we have is like representative of the entire brand in general. We have the null hypothesis is that the two brands have the same runtime, and the alternative is that the two brands are actually different. Okay, and here I'm going to use a not equal sign, meaning that, you know, it'd be interesting to us if brand A has a shorter runtime than brand B. It's also interesting to us if brand B or brand A has a longer runtime than brand B. So it's either result is interesting. And so we want to find the p-value, okay? And again, the question is, if brand A and brand B are actually the same, could just by randomly selecting different batteries, we end up getting an average difference, a difference of 6 minutes between the two averages. And if it's possible, what's that probability? Okay, so we need to get our values into vectors that we can then plug in to conduct our t-test. So to extract vectors of values, what am I going to do? I do batteries, and I filter to brand A. I select the column I want, which is runtime, and I select pull. Okay, so again, kind of going back to the data way back here. So remember, I pivoted it longer, and so I'm just filtering to the rows that have brand A, and I'm selecting this column runtime, and I'm just pulling out these numbers. Okay, that's what this command is. Okay, so I pull the thing, and I store this into just this thing called brand A. And so this is just a vector of values, right? And so we're familiar with vectors, yeah.
Is there another way to do that without just subsetting?
Yeah, you could subset, okay? So you can, I'm a big fan of dplyr, so you can, so I did this, but yeah, you can certainly subset, and you can, subset batteries, and you'd subset the rows where brand is equal to brand A, and then you'd subset just the column runtime and get that out, okay? But here, and so I do the same thing for brand A, and I do the same thing for brand B. And so I get these vectors of values, all right? And they're stored, the brand A is a vector of these 12 values, brand B is a vector of these 12 values. And then the command I run is called t-test, all right? So t-test is used to compare the means of two groups. And I compare brand A versus brand B. And it does the calculations, and really the row I want us to kind of look at is this top row for the p-value, right? It says, this is our test statistic t. We have this many degrees of freedom. Don't worry about that right now. But our p-value is 9%, 0.09, 0.09. So the p-value for our test is around 9%. And so that means if brand A and brand B do truly have the same mean, okay, if that null hypothesis were true, and you're just selecting batteries at random, could you end up getting a difference of 6? And it says, yeah, that could happen, and it's going to happen around 9% of the time. Okay, so not like an incredibly high probability, but it's also not a really small number either. Okay, if somebody says, this roller coaster has a 9% chance of failure, he would not get on, right? Okay, it's not guaranteed that it's going to fail. Most of the time it won't, but the fact that you'd be like, oh, I don't want to go on a roller coaster that's going to fail 9% of the time, you probably, I guess, depending on your risk tolerance, you probably wouldn't want to go on that ride. Okay, so that's basically what I wrote here. So if there's one factory that produces both brand A and brand B, is it possible that just by random luck we end up with 12 batteries in brand A that will have a mean of 123 and 12 batteries in brand B that have a mean of 129? Yeah, it's possible. How often does it happen? It happens with around a 9% probability. Okay. Is that a big or small number? It's not a huge number, but it's not so small that we would just want to ignore it. And if we use 5% as our threshold between what's big and what's small, 9% would fall on the big side. And therefore, that means we are not going to reject the null hypothesis. Okay? So in our case, the p-value is large, and that means our data could be easily observed by randomness, even if the null hypothesis were true. And even if our observed data doesn't match the null hypothesis exactly, meaning we didn't get two samples where the mean is exactly the same, we're saying, this difference of 6 minutes, not that huge, has a pretty high chance of happening by random chance, okay? And so we would not reject the null hypothesis, all right? So we just can't make a definitive conclusion. It's possible that brand A and brand B have the same mean, and our data is a result of random chance, okay? It's also possible that they're different, and we just haven't collected enough data. Okay, that's also a possibility. That's something. Anytime you say, "Well, it's inconclusive. I don't have data to say they're different," we also have to take into account that maybe I just haven't collected enough data, and that can be a frustrating thing. Maybe you need to collect lots of data to detect a difference because there is a difference, but it's a really small difference. All right, we don't know. I'm going to run out of time. Let me give you your last view quiz answer, which is the letter E. I've given you two already, right? Okay. Last one is E. E as an elephant. E as an elephant is our third view quiz answer. One thing is we're not allowed to use this phrase, we accept the null hypothesis. So just because we did not reject the null doesn't mean that that null hypothesis is true, right? We can't say brand A and brand B have the same mean and that they're coming from the same factory or something like that. All we can say is that with only 12 batteries from each brand, getting a difference of 6 minutes is not that big of a deal, not enough to make a definitive conclusion. I tried this out and I said, okay, what if we collected a lot more batteries? And so here I just made these much bigger vectors and I just, again, fake numbers. And here I said, let's run way more tests. We have brand A, we put in 36 batteries from brand A, we ran them all. We did 36 batteries from brand B, we ran them all. Okay, and we're gonna say, okay, after 36 batteries, the mean for brand A is 123, and after 36 batteries, the mean for brand B is 129 still. Okay, so we're still getting a difference of 6 minutes, but now we have a lot more data to kind of back this up. All right, so here I just put them in directly. Again, you could imagine importing a data set, filtering it, and pulling the data to get your vectors. Okay, and when you run a t-test here between these two samples, now we get a p-value of only 1%. P-value of only 1%. So now we're saying, okay, if brand A and brand B are the same, could I get 36 batteries where the average is 123 and another 36 batteries where the average is 129, just kind of by randomness? And now the answer is, yeah, it could happen, but it's like really unlikely now, okay? So it's kind of like going from, all right, if I flip the coin 20 times and I get 12 heads, that's not that weird, right? 60% heads out of 20 flips, not that weird. Okay, but what if I flip the coin 2,000 times and I get 1,200 heads? Okay, we're expecting around 50% heads. So 20 flips and getting 60% heads, not that weird. 2,000 flips, or let's say 2 million flips, okay? 2 million flips and I get 60% heads, meaning I get 1,200,000 heads rather than something around 1 million heads. That would be really weird, right? So even if I'm getting the same difference of 6 minutes, the fact that I have way more data says, you know what, this can't just be the result of randomness. Not that it can't be, but it's like really unlikely to be the result of randomness. And therefore I'm going to consider the fact that, yeah, you know what, brand A and brand B probably are actually different. That's an easier explanation for this, the difference that we're seeing between batteries here. Okay, well, we'll go ahead and end here for today. We'll talk more about some of this hypothesis testing stuff next week. I hope your group meetings are going well. You're able to find data, and yeah, I look forward to our proposal meetings next week, and we'll see you then. Have a great weekend.